In this video, we'll be focusing on mole conversions, specifically mole to representative particle conversions. So as you can see, we have 4 problems listed here, and all of them involve moles. The directions say to convert the mole values to molecules. So that's what we'll be doing. Before we begin the problems, let's take a look at the mole map to remind us of the units and the conversion factor we'll be using when solving these problems. On the mole map, the mole is shown to be in the center. It should be understood that when you see the mole on the mole map, it always means 1 mole. Now, since we're converting moles to molecules, a molecule is a representative particle. So we'll be going in this direction. In addition to being a molecule, a representative particle could also be an atom, an ion, and a formula unit. So any of these labels falls under representative particles. So remember, 1 mole equals, since we're counting particles, equals always 6.02 times 10 to the power of 23 particles. Since we're focusing on molecules, that's what we'll put as our label for this number. We're going to be using these values and these labels in our calculations. Let's try problem number 1. We will be using dimensional analysis to solve these problems. The first thing we'll do is write down the given value, which is 2.0 moles of hydrogen. Hydrogen, remember, is a diatomic molecule. That's why it has 2 as a subscript. Then we'll set up our dimensional analysis table. So since moles is in the numerator, we're also going to put moles in the denominator. And we'll put molecules in the numerator, since we're converting to molecules. There's no official label for molecules, so just for the purposes of keeping things a little short, I'm going to use MLC to abbreviate molecules. So we'll put molecules up here at the top and plug in our numbers. So it's 1 mole equals 6.02 times 10 to the 23rd. And hopefully you remember from previous dimensional analysis calculations that to solve this problem, you will need to multiply the top and divide by the bottom. So the moles cancel, and we're going to have molecules in our answer. Let's get our calculators out to solve. 2.0 times 6.02 EE, which stands for exponent 23, equals 1.204 times 10 to the power of 24. Remember to use significant digits in your final answer. Our given value has 2 significant digits, so we're going to round our final answer also to 2 significant digits. So 1.2 times 10 to the power of 24, and our label in our answer will be molecules, hydrogen. Let's try problem number 3 as our second example. It will be set up the same way because we're still converting from moles of nitric acid in this case to molecules of nitric acid. So 0.75 moles is the given value. Now we're going to set up our dimensional analysis table. Remember, moles need to cancel, so we will put moles of nitric acid in the denominator, and we're converting to molecules, so that label needs to go in the numerator. Let's go ahead and cancel out the moles of nitric acid, and we're going to, again, multiply the numbers up at the top. So 0.75 times 6.02 EE, which is the exponent, 23. And that equals 4.515 times 10 to the power of 23. Remember, we will still be using significant digits to record our final answer, and our given value has 2 significant digits. So we're going to round the calculator answer to 4.5 times 10 to the power of 23. molecules of nitric acid. So that's how you do mole to particle or mole to molecule conversions. Now let's take a look at the opposite type of problem. In this section, we will be converting particles to moles. So remember, representative particles can be atoms, molecules, ions, or formula units. All of these are potential labels that you could encounter. So let's take another look at the mole map to make sure we understand the units that we'll be using to perform these calculations. So because we're starting with representative particles and converting to moles, on the mole map we'll be going in this direction. We will still be using 1 mole equals 6.02 times 10 to the 23rd particles, whether it be atoms, ions, molecules, or formula units. Let's use number 5 as our first example of this type of problem. So we'll start the same way where we write our given value, 6.02 times 10 to the power of 23 molecules of NH3. NH3 is ammonia. And then we're going to set up our dimensional analysis table. This time, we want to cancel out the unit molecule. So molecules will be in the denominator of our setup, and the mole will appear in the numerator. So we're still using the same conversion factor. 1 mole equals 6.02 times 10 to the 23rd. So notice this time we're going to be dividing by Avogadro's number. The molecules of ammonia cancel, and when we divide, notice the numerator, 6.02 times 10 to the 23rd, is the same as what's in the denominator. So that cancels. The answer here will simply be 1. We still need to use significant digits though. So because we have 3 digits in our given value here, 3 significant digits, we'll also have 3 significant digits in our final answer. So our final answer is 1.00 moles of ammonia. Let's try number 7 as our second example. Once again, we're going to write our given value, 1.5 times 10 to the power of 20 atoms of magnesium. Now that we've set up our dimensional analysis table, well, you should be able to tell that atoms will be the label that is placed at the bottom of our setup, and moles of magnesium will go at the top. And it's still going to be 1 mole equals 6.02 times 10 to the 23rd. And once again, because we're converting from atoms to moles, we'll be dividing by Avogadro's number. So 1.5 EE, which is exponent 20, divided by 6.02 exponent 23 equals 0.000249. Okay, so we want to put this value into scientific notation and use significant digits. So our final answer for this problem comes out to 2.5, 2 significant digits in this value, 2.5 times 10 to the power of -4 moles of magnesium. And that's how you convert between moles and representative particles.